The fourth question is about the simple regression with only one regressor, but that is endogenous. Part A, it is too simple. I'm asking you what kind of assumptions you need. Uh, you know, you need exogeneity and you need relevance. Okay, exogeneity and relevance are your required assumptions. And part B, identification. You have to show that. So here the function gi, the moment function is defined as 1zy minus alpha minus beta xi. Here you have to note that like many of you are just using this single moment, right? So it is right, it is a moment, but you have to realize that you have two unknowns, right? So this single moment is not enough to identify the two parameters. So then you have to additionally use another moment, right? That is assumed in the question. And intuitively speaking, this is related to this guy and this is related to this guy, right? So we learned that as location normalization. So this is we have moment function that is pretty straightforward. Oh, and then we know expectation of g theta 0 is expectation of 1 and z times ui, which should be 0 by these two assumptions. Okay, now you have to show that this is unique, right? For uniqueness, I'm going to think about this linear equation. So if you think about it, we may write this as 1zy minus expectation 1z times 1 and x transpose theta, right? Theta is alpha and beta, right? You are familiar with this. Usually, let's write this as A and write this as B. Then we get so this equation is 0. So then if you think about B theta equals to A, then and if rank of B is 2, then the solution is unique. Okay, we proved it in the previous chapter. So we are going to assume the rank equals to 2. That's the full rank assumption implied by the relevance assumption. Okay, all right. Now let's think about C. Find the optimal weighting matrix. This is another trap, right? So you have two parameters, alpha and beta, and you have two moment conditions. So it is, say, 2 by 1 and it is 1 by 1. So it is 2 by 1, two moment conditions. So you have exact identification. Sometimes some textbooks call this just identification, just identified. And then in this case, we know weighting matrix does not matter. That means any weight is optimal, right? So because it does not affect anything, so any weight is optimal. There is no difference. So I suggest identity matrix, right? 2i2 identity matrix, 1 1 0 0, right? That is my suggestion. You may think about any other any like symmetric and strictly positive definite matrix. That's also okay. That is also optimal. But of course, you don't need to, right? You don't need to make it more complicated. Now then, let's think about the GMM criterion function. Let's say L hat theta will look like GI theta transpose. I will ignore weighting function, that does not matter. So we will have something like this, right? So I'm using optimal weighting function, the easiest, most convenient weighting function. And then the first derivative will be times like this. Okay. By the way, it is. So if you do the simple math, you are going to see that this is minus summation of 1 and z and 1 and x transpose, right? This is the first part. And in the second part, you are going to have z, excuse me, 1 and z times yi minus 1 and z times 1 and x transpose theta. Okay, it is what we did here. It's like a and b. Okay, so I'm going to write this as a, and let's write it as b. Okay, then the first order condition is b transpose a minus b theta hat n is 0, right? So that is the first condition. When you plug in theta hat here, this derivative is a function of theta here only. Okay, so that means if you write this out, expand it, you are going to get this, and then theta hat n is b transpose b inverse b transpose a, right? By the way, let's remember a was 1 and z I y I, and b was 1 and z and 1 and x transpose. Okay, so now think about this. This is 2 by 2 matrix, and we know its limit is full rank. So you can write this as b prime b inverse will be b inverse times b transpose inverse times, so b transpose a. So it cancels out. So it's pretty simple. B inverse times a. That is theta hat, right? So I will just solve it out. I will just calculate b hat b. Let's think about matrix B. It is sample average of 1 z x and x times z. Okay, so this is what we are going to have. And for simplicity, like it's actually confusing later, so I'm going to write this as 1 x bar z bar and write this as, say, c bar, right? C is just x times z, right? To simplify all the things. And then b inverse is 1 over c bar minus z x bar times z bar. And here c bar minus x bar minus z bar and 1. Okay. Now we are going to multiply that to a. So again, b inverse was 1 over c bar minus x bar z bar, and here c bar 1 minus x bar minus z bar. Okay, let me check. So right. And then a was this and yizi, this. So I will also simplify this to y bar and yz bar. Okay, multiply them. B inverse times a is something. By the way, let me do this first. C bar minus x bar z bar is, right, it's x times z total bar minus x bar times z bar, right? This is finite covariance, right? This is covariance, sample covariance between x and z, right? Because you can rewrite this as xi minus x bar and zi minus z bar. Okay, so it's a simple thing. So I'm going to write this as covariance for simplicity, and then multiply c bar x bar minus z bar 1 times y bar y z bar. We are interested only in beta, so I am going to ignore this part. It does not matter. And we are going to calculate this, the second element. Then you know it is this guy. Okay? So then beta hat, the second element, equals, so the denominator is xz bar minus x bar times z bar, and numerator is yz bar minus y bar times z bar. Okay, so that means it's 1 over n summation yizi minus sample average of yi, so sample average of zi. Same thing. Same thing again, like just change y with x minus summation. Okay, like this. So if you're curious why it is, it changes, I say. So if you think about yizi minus yi times the basic statistics. So I may write this as minus yi times z bar, right? So just I use this notation, and then means the second term can be written as 1 over summation z bar times yi, right? Doesn't matter. You can just plug that inside the sample average. It is constant, right? And that means you can factor out this summation and this summation. So it becomes summation. First term is yizi minus second term is yiz bar. So it is yi times zi minus z bar. Okay. And then also you can show that it is y and zi minus z bar. So that is covariance between sample covariance between z and y. And of course you can do the same thing for x and z in the denominator. Okay. So we show that the closed form solution is very simple actually. And remember, the OLS, simple regression OLS, had the form of minus x bar yi over this form. It was OLS. Just so what we are doing here is we change this part as z, and we are going to change one of the squares to z. That is the IV regression, right? Compare the IV regression coefficient with OLS. And also remember, the identification result was covariance between yizi over covariance xi was beta 0, right? So then its sample counterpart is exactly what we are calculating. Okay, so this is another way to interpret the GMM estimator. So estimator itself is pretty straightforward. Now let's think about part E. So in the previous calculation, we are calculating finite solution, finite sample solution, right? When you have finite observations, how can you calculate the beta? Now in part E, we are thinking about asymptotics, asymptotic variance. We know it is G transpose omega inverse G inverse if weighting matrix was optimal, right? We are choosing optimal weighting matrix, so we are going to get this. And in our case, G is defined as, remember in general, G was defined this way, and in our case, it was minus expectation of 1z times 1x transpose. Okay, so it is minus 1 expectation of z and expectation of x and expectation of x and z. That is g, and omega is expectation of gi theta 0 times gi theta 0 transpose. That was omega, and we know it was ui squared 1zi and 1zi transpose. And in this question, I assume that the error term is homoscedastic, right? So it will look like, let me erase it. Oops. Sigma squared and 1 expectation of z, expectation of z, expectation of z squared is omega. Okay, we are going to calculate G transpose omega inverse and G and total inverse, right? By the way, G is invertible, non-singular, okay, right? It's a full rank. So then that means we can write this as G inverse times omega inverse inverse. So that goes back to the original, and we just need to calculate that. So we have to invert G first and then multiply them. We are going to think about G inverse, right? G inverse is 1 over expectation xi zi minus expectation xi expectation zi. Here, and here expectation xi zi minus expectation xi minus expectation zi and 1. This is G. By the way, here, again, the determinant is covariance. It is literally the definition of covariance between x and z. So I will just write it as covariance. Okay, so we are going to calculate G inverse omega G transpose inverse. By the way, transpose inverse is its transpose. That should be simple. Let's do that. It is 1 over covariance squared. So these covariances will be just taken away. Expectation x z. I will drop subscript I. Minus expectation x minus expectation z 1 times sigma squared should be also factored out. 1 expectation z expectation z expectation z squared times expectation x z minus expectation z minus expectation x 1. You just do the algebra, right? Knowing covariance squared, and let's do this. Multiply like that. Expectation x z minus expectation x expectation z covariance, and expectation x z times expectation z minus expectation x times expectation z squared. Here minus expectation z plus expectation z, so it will be cancelled out. Pretty interesting. And here minus expectation z squared plus expectation z squared. Expectation xz minus expectation z minus expectation x 1, right? Now then, one more calculation. By the way, we are interested only in the variance of beta. So the result of this algebra will be 2 by 2 matrix, but we are interested only in this guy. Okay, so that is pretty simple. This is 0, so we can just multiply this to this. So this part will be expectation z squared minus expectation z total squared. That is variance of z, right? It is interesting, right? So as a result, combining also this part, we just found that asymptotic variance of beta hat is sigma squared over covariance x and z squared times variance of z. This was the variance of the IV estimator, IV regression coefficient. Okay, let me manipulate it a little bit. So, by the way, the correlation coefficient rho is defined as covariance between x and z divided by standard deviation of x and standard deviation of z. This is the definition of correlation coefficient. That means if you square this, you are going to get covariance squared divided by variance of x and variance of z. Okay? Right, of course here x and z. So then, from here, if you replace this, you may replace this like sigma squared over rho squared times variance of x, variance of z, right? If you move this the other way, then you get covariance squared times variance of z, and then you are going to cancel this out. So in the end, the variance of beta hat is 1 over sigma squared, 1 over rho squared times sigma squared over variance of x. All right. And what is interesting here is this much is the variance of OLS, and then this is kind of weight some multiplier. Then what is it? By the way, you know the correlation coefficient is always less than 1. So that means its square is always between 0 and 1. Like they may equal, but let's ignore equality. And square is less than 1 and positive. And that means 1 over squared is greater than 1. Right? That means your IV regression GMM estimator's variance is greater than, multiplied by this much, has a greater variance than the OLS estimator, right? So it has the same variance only when rho is 1, which means your instrument is perfectly correlated with yourself, your regressor. So that's the only exception. That means just your x is exogenous, right? So whenever you are using an instrumental variable, you lose efficiency. That is because your controlled variation is not perfect. Your controlled variation, so remember in the identification chapter, I explained the controlled variation. You are trying to capture the controlled variation of x using your instrumental variable. That depends on your correlation coefficient. Okay, so you can interpret this pretty intuitively. Okay, good.